There you go. Okay. This is something we had in the 10th grade, and we may have even talked about, did we talk about this year? Phase of matter, solid, liquid, and gas, right? So we already had the chapter on solids, and this is something they might even teach in 4th grade, you know? But they might not do some of this. In 4th grade, do solids have a definite volume? And the answer is yes. Do they have a definite shape? Yes. They a lot of times don't want you to know the reasoning. They just want you to memorize the chart. And does anybody know why? Why was a solid have what? Whoop. Oh, it didn't change its shape. Right? It didn't change its shape. Why not? And so why do we think that solids have a definite shape? Definite shape and definite volume. It's the same reason. And you look over here, if you could draw a concept of solids, we think that their particles are incredibly close together, and there's no exchange, and you can't move from one place to another. They might be vibrating, but they're not going to exchange places like that. And so solids have a definite shape because they're attracted to, everybody's attracting everybody, and they can't get out of that shape. They have a definite volume. You can't compress them because there is no empty space between them. And it says here, are you a fluid? No, because fluids can flow and solids don't flow, and the particles are very, very close. So we just got done with a chapter on solids. Now, the chapter we're doing now is on liquids. Now, let's think about this. Do liquids have a definite volume? If I have 100 milliliters of water in a tall cylinder and I put it in a big fat bowl, is it still 100 milliliters? And it is. Why would that be? Why would they have a definite volume? And look over here. This is interesting. Why don't they have a definite shape? See, to me, this is the same reasoning, that they have the definite shape, definite volume. There's something a little different. But if I ever had to draw a liquid, I would draw it pretty much like a solid. How do I know that? Because can you compress a liquid? You're going to find out in the last 2 pages of this chapter. It's called Pascal's principle, and we're going to talk about that today. But if you try to compress a fluid in an enclosed container, you can't compress it. But whatever force, whatever pressure you put on it, it'll be distributed to every wall. And that's how I'm gonna get home today. I'm gonna when I go home, I'm gonna get in my car and I'm gonna put on the brakes a few times. And in my brakes, there's a fluid. There's a fluid in the brake line, brake fluid. And I'm gonna try to compress it. The fluid, you can't compress it. But what's gonna happen to the force that I use, the pressure that I use to compress that fluid, it's gonna go from where my foot is to where?
The brake calipers.
Yeah, to the brakes, right? And I'm not going to touch the brakes. I'm not going to touch the wheels with my hand. But when I push my foot on the brake, that fluid is going to go whoop, and all that pressure is going to be distributed to every one of those wheels, and it's going to produce a huge amount of pressure. It's going to force that tire, the brake shoes to come in and stop my car. And we're going to learn about that. It's called hydraulics. Ever heard of hydraulics? So you can see on a backhoe, you know, sitting on there just moving a little lever. You move a little lever, and all of a sudden the shovel, there's like a 200 shovels full of dirt. How are you doing that? The person's not even sweating, you know? That's hydraulics, isn't it? So we'll talk about that next time we come together. Not tomorrow. Tomorrow's remote day, okay? Okay, so anyway, we know that liquids are very close because you cannot compress them. But we know that there is at least some movement by layer. There is some kind of movement because it can flow and it can actually take different shapes. But I would not say like elementary teachers do, and I wish they didn't, but particles of solids are really close, particles of gas are really far apart, and particles of liquids are kind of in between. That's the Goldilocks principle again. That's not true. I've never seen evidence. There are science books that do that. They'll actually say, well, it must be halfway. Yeah, halfway. But I can't compress. I can't compress a gallon of water into half a gallon of space. They can't be halfway. So I want to start with that just so you know where we're at. We're finishing solids. We finished solid. We're doing the liquids. And when we get to here, that's a whole other ball game. When we get to this guy, that's a whole other ball game. Because I might go in the water, and the density of the water might be very similar here, 10 feet down, 20 feet down, a mile down, the density might be very, very similar. But when we get to the next chapter on gases, I had to think completely different. I'm living at the bottom of an ocean of air, and that air on top of it is compressing the other air. I'm living at the most dense air on the planet. Now, I don't say that for water. For water, it doesn't change density too much. The only thing that can change density, temperature can change it a little bit, and the salt content can change it a little bit. All right. Excuse me. So what I want to do is, let's make sure we get this other material. Archimedes' principle, one more time. Here's an object that seems to weigh 3 newtons. That means the Earth is pulling on it down with 3 newtons of force. So it weighs 3 newtons. Now, when I put it in the water, the spring scale says, no, I guess not. I guess the object only weighs 1 newton. And you know that something's wrong there, don't you? That's called the apparent weight. It looks as if it only weighs 1 newton. But we know the Earth is still pulling down with 3 newtons. So why does it appear to weigh only 1 newton? And if you were in the water, it would feel like it only weighed 1 newton. Yes? Now, yeah, there must be, even though the Earth's pulling down, there must be something else pushing up with about 2 newtons, because 3 down and 2 up is 1 down. So the apparent weight is only 1 newton. Now, Archimedes said the amount of buoyant force, measured in newtons, right? He didn't know about newtons back then, but the apparent force, the buoyant force, is equal to the weight of the water displaced. That's kind of weird. Who would even think about weighing the water? I understand if I took the volume of that water, put it in a graduated cylinder, that would tell me the volume of that material, wouldn't it? That's the principle of water displacement. But who would even think about weighing the water? And you'll find out later in Newton's laws that when you push water, when something pushes water, displaces it and pushes it, what's the water going to do? When you push something this way, what's it going to do? That's Newton's third law. For every action, it's an equal and opposite reaction. So if you displace that water, you push the water to the side, it's going to push back. And that's that buoyant force we're talking about. And what direction is always buoyant force in? Up. All right, does everybody understand that? So even this drawing here, when you do your homework, this drawing here, if I look at up here at the top, the amount of pressure on the top is less than this. It's greater on the bottom because it's deeper. Remember depth? And so what's the difference now? What's the difference in pressure? Let's say it's 1 down and 2 up. There's still going to be a buoyant force of 1 up. If I go down deeper, well, now you're deeper, so there's more pressure on you, but there's also more pressure on here. Well, what's the difference in pressure? 1 up. 1 up. So even if I go deeper, I still get the same buoyant force. And that's going to be important to you, okay? Everything has to do with that volume right there. What aspect of that cube displaces water? The color of it? The smell of it? What is it? The volume. Volume is everything with displacement. And volume is everything with buoyant force. And so if I take this, even though the volume's here or down here, I still get the same amount of buoyant force, even if I take it down deeper and deeper and deeper. And by the way, do you understand why you can't go to the bottom of the ocean without getting killed? I think I'll just say, hook me up. Here, give me an air tank and hook him up to a stone and let me go down a mile down. You're going to die. And what's going to happen is, as you go down deeper and deeper, you're going to have more and more weight of water. The weight of water above you is going to be a huge, huge amount. And it's going to crush you. That's why we have to build the submarines very, very well. They have to be built really well to withstand the huge amounts of pressure. I do like some of the movies now. They've been, a lot of them have scientific advisors. And whenever you see a submarine like blow up, you ever seen that? They have some pretty good effects. You ever seen that in movies? What happens to a submarine? They're down really deep. They go, boom. Okay, so explosion for a while, it makes the sides and everything go out. Boom. But then what? The huge pressure comes in, it implodes, doesn't it? Explode, implode. And so I think they're doing a pretty good job on that. All right, Now, I want to show you, by the way, I want to tell you about, I had to make a decision on what to do on remote day. I was not chosen to be one of the Zoom people, and not on Wednesdays. So what I'm going to do is, by 8 o'clock tomorrow morning, you'll see the assignment I have for you during my class. And remember, go 1, 2, 3, 4, 5, 6. So you'll be the second hour of the morning. What is that, 9:15? Somewhere around 9:15 to 10:15, you'll be given an assignment to do. And what I'm going to do is, I'm going to post the worksheet on Google Classroom, and I would like you to scan it and return it to me in Google Classroom. But I would also like to say, I actually have already printed that sheet off. So what I would like to do today is I wouldn't mind giving you the sheet today, and then you just have to scan it and give it to me during that hour tomorrow. And then if you wanted to get it finished tonight, you could actually use that hour and work on your homework, your other homework assignment. But that's what I'm doing, and so you'll see it on Google Classroom. But I actually have the sheet already printed, and so before you leave today, I'll go ahead and give everybody one of those sheets. And that's all I have for you. If you finish the sheet tonight, you could just work on your other physics homework during that hour, and that'll be it. Okay, so what I'd like to do, I'd like to show you a drawing, and this is what I'm going to draw today. I'd like, after I get done with this, I would like to get back to and do some demonstrations too. I have this has to do a little bit with the worksheet you're going to be doing, so I'm going to go ahead and do this for you. I want you to think about a kind of a scenario. It's kind of a weird scenario, but let's imagine we have some water here, and let's say I have a 1 liter. I have 1 liter container, and let's say the first 1 liter of water. Let's do that. 1 liter of water. Okay, now I want you to think about this. This is going to be a very, very telling picture. Okay. What is the mass of this object? What is the mass of this object right here? Everybody should know. 1 kilogram. We did a project on that, didn't we? All right. What is the weight of this object right here? 10 newtons. 10 newtons. Oh, you sound like a physics student now. All right. What is the volume of this cube? Remember I talked about the big 6? What's the volume of this box? Uh-oh. You answered that one so fast. This is actually the easiest question. Colleen, you know. Yeah, you do. Okay, since you said it. It's 1 liter, isn't it? Wait, is that right? It's 1 liter, right? That's volume, isn't it? Now, let me ask you this question. What is the volume of water that's being displaced? What's the volume of water that's being displaced? Jessica. I'll give you a clue. It used to be sitting right here, and now it's not there. It's sitting somewhere else. What is the volume of water that's being displaced? Yes. Walker, what is the mass of the water displaced? What is the mass of the water displaced?
Is it 1 kilogram?
Yes. What is, Sarah, what is the weight of the water displaced? Man, you guys are sharp. This is great. And the final question, Tucker. What is the amount of buoyant force on this object?
10 newtons.
How'd you know that? Who said that? Well, who else said it? Okay, somebody actually said it before you, but and I've said it many times. But before you were born, I said it. But even before I was born, Archimedes said it. So that isn't that Archimedes' principle?
Yeah.
The buoyant force is equal to the what? To the weight of the water displaced. Okay, so now we're going to draw a little diagram here. And so is everybody okay on that? Now, I had a lot of questions, wasn't it? Now, I'm going to do it for more than one object. I'm going to see what happens when you do that. So if I had to draw a diagram now, and I would say this is all true. Got that? It's all true. And so what I'm going to do is I'm going to draw a diagram that represents 10 newtons, and that's the buoyant force. Okay with that? Buoyant force is up. Is there 10 newtons of buoyant force on this guy? Okay. Now, is the object, when I let go of it, is it going to sink, float, or stay right there? And that's a separate question than Archimedes' principle. Archimedes' principle tells me this. What is the weight of this object? How much is the earth pulling down? How much is the earth pulling down? You told me its weight was 10 newtons. Is that right? So what's it going to do when I let go of it? Can you see me through the aquarium, MSA? Okay. All right. What's it going to do? It has a buoyant force on it with 10 newtons up, but the earth pulling down with 10 newtons. So what's it going to do when I let go of it? It's going to stay right there. If you ever do become a scuba diver, they actually have a weight belt. You put a weight belt on there because most humans, the average density of most humans is somewhere a little bit less than 1. You tend to float. There are some people that have very little fat and their body's shape. There are some people that are sinkers. But most people, their density is very close to water and maybe a tiny bit less than that. And that's why you tend to float a little bit. So as a scuba diver, I need to put a weight belt on. All right, I got my tanks and stuff, and I put a weight belt on. It's going to make me sink. But I also have a vest on called a BC vest, a buoyancy compensator. And what I can do is you can push a little button, and some CO2 gas would actually go into that vest. Now, how in the world is that supposed to help me? How's it going to help me to put air into a vest? I'm sinking, I put air into the vest, I stop sinking, and I sit there. I'm neutrally buoyant. If I'm sitting there 100 feet below the surface, and I'm not going down or up, which one is greater, buoyant force or weight?
They're equal.
They have to be equal. How did I make it equal? Before, weight was greater than buoyant force, but when I put some air in the vest, I became neutrally buoyant. What did that do? I mean, I already had the CO2 in a compressed tank. I still weigh the same. What do you think, Liam? Let me ask you this question. Let's say 2 of you are going to go in the water, and I give both of you a life jacket, okay? Now, let's say you tend to almost sink, and I give you a life jacket, and you don't sink, do you? Your head stays above water. You say, well, that's what a life jacket's supposed to do. Well, how does that work? I just added more weight to you. If you're kind of a sinker anyway, and I give you a life jacket, you're going to weigh even more. So why would that help you? And here's my other question is, let me give you another life jacket, give me another person another life jacket, identical in size, except it's made out of lead. I give both of you the life jacket, one of you is going to sink like a rock, and one of you is going to float. Now, I got to think about that. I want you to think about it. What do you think?
Is it because it's less dense than the water?
Yes, density has something to do with it. You're right. True or false? The lead life jacket actually increased the buoyant force on you. Now, I need you to look right at me, okay? Because this is a critical day. When you put a lead life jacket on somebody, it actually increases the buoyant force on that person. True or false? True, because when you go into water, what did the lead jacket do? It displaced water. You actually get more buoyant force by me giving you a lead life jacket. But that's a different question about whether or not you're going to sink or float, right? What made the person sink? Weight was greater than the total amount of buoyant force. How about the other life jacket? I actually made you weigh a little bit more, but the buoyant force was greater. That's how they do it. That's how a life jacket works. So when I put a gas into a BC vest, buoyancy compensator vest, I'm actually displacing more and more water, aren't I? And that gives me more and more buoyant force. All right, so now you got to fight this because this thing is experiencing an upward buoyant force, correct? But if I let go of it, it doesn't go up. It doesn't go down. That's called the principle of flotation, isn't it? Now, let's go another one. Let's build a 1 liter box, and I want to fill it with iron. Okay, by the way, the density of water is 1 gram per cubic centimeter. Okay, does anybody know the density of iron? It's about 8 grams per cubic centimeter, okay? It's about 8 times more dense than water. Okay, so here we go. What is the mass of this 1 liter block of iron? What is the mass? All right, I need somebody to say, raise your hand, take a chance. I think I know. Jeff, is that your hand?
Well, so 8 kilos.
Say it again.
8 kilos.
That's exactly right. That's exactly right. The mass is 8 kilograms. Now, since you're on a roll, what would the weight of this iron box be?
Would be 80 newtons.
Oh, man. This is great. Okay, now, you want to keep going? It's like you're on Jeopardy. All right, ready? What is the volume of this cube?
Bigger.
Yes. What is the volume of water that is displacing?
8 liters.
Yes. What is the mass of the water that it displaces?
8 kilos.
Yes. Oh man, he's going to win this game. What is the weight of the water being displaced?
10 newtons.
Yes. What is the buoyant force on this object?
10 newtons.
Yes. This is absolutely wonderful. Now, so what we're going to do is we're going to draw a 10 Newton buoyant force here, same size as this one, and your final Jeopardy. Ready? Will this object sink or float when I let go of it, and why? You bet all your money on this, didn't you?
All the marbles.
What?
It'll sink because the buoyant force is way less than the mass of the object.
The mass? Is mass in the vector world?
The weight,
What is the weight?
80 newtons.
Yes.
So
Hey, you kept your money.
the buoyant force is only 10 newtons.
Hey.
And
Excellent.
the weight is only
Excellent. Excellent. Now, take a look right here. You can get fooled on this because here's 1 liter of water, here's 1 liter of lead. And which one has the greater buoyant force on it? And you better fight this because you're going to say, oh, I know it. No. These have the same buoyant force on them, didn't they? Because they're both displacing 1 liter of water. That's a different question. Archimedes' principle is different than whether or not somebody's going to float or sink. You understand what I mean by fighting it? You got to fight that. Here's why, and you're exactly right. How many did you ask? 8 in a row? That was wonderful. It's going to sink because the weight is 80 newtons and the buoyant force is only 10. The net force is 70 down. Oh yeah, it's not only going to go down, it's going to go down and accelerate. Yes?
So no matter what material or anything, as long as you drop 2 objects of the same volume?
Yes.
They'll both have the same
Yes.
force?
Yes, and that's Archimedes' principle. Whether they float or sink, though, is a different question. Oh, what a great day. This is a great day. Now, let's do another, okay? Let's do 2 more. How about 1 liter of air? And I will tell you that it's about, the density is about 0.001 grams per cubic centimeter. Okay? All right, so who wants to take me on a run here? Who wants to go on a run like Jeff did? I'll ask the questions, you answer it. You already answered 3 today. Liam, you answered. You had a great, I know you two seem to understand it. How about somebody that's a little shaky on this? Yes? You want to do it?
Okay.
Okay.
Sure.
All right, ready? What is the mass of this object?
The mass would be 0.001 grams.
That would be per cubic centimeters, but
Oh,
there's 1,000 cubic centimeters
Yeah.
here.
So then it would be 1 gram.
Okay. Also known as 0.001 kilograms, but you're right, 1 gram. All right, that's the mass. Ooh, what's the weight?
The weight.
And I, huh?
0.01 newtons.
Yes. What is the volume of this cube of air?
A liter.
Yes. What is the volume of water that it's displacing?
A liter.
Yes. What is the mass of the water it's displacing?
A kilogram.
Yes. What is the weight of the water it's displacing?
10 newtons.
Yes. What is the buoyant force on the cube?
10 newtons.
Yes. When I let go of this object, will it go up, go down, stay right there, and why?
It would float because
Would it go up, down, or stay right
it
there?
would go up.
Yeah, when you say float, that means you don't go up or down.
It would go up because the weight is significantly less than the buoyant force.
Yes, the weight is only, it's hard for me to draw that little guy. The weight is only 0.01 newtons, is that right? You're exactly right. See, Jeff, see what you started? That was great. And you gave them, you empowered them to say, well, I can do that. Do you understand that? Are you understanding the Archimedes principle has to do with volume? The more water you displace, volume, the more buoyant force you get, period. All right, one more. Let's do one more. Okay, let's have a box of nothing. A box of nothing. All right, Emma Shea, you can do it. Emma Shea, we have a 1 liter box of nothing. Okay? Are you ready? What is the mass of 1 liter of nothing? What is it? 0 kilograms, right? What is the weight of a liter of nothing? 0 newtons. What is the volume of water being displaced? Hang on, I didn't hear that. What is it? What is the volume of water being displaced? I'll give you a clue. What used to be right here? Yes. What is the mass of the water that's being displaced? Kilograms of mass. All right, that's right. What is the weight of the water displaced? On a kilogram is mass. You always take kilograms times 10 to get newtons. 10 newtons? Okay, what is the buoyant force on this a box of nothing? Yes, so let's draw that. So there's 10 newtons of buoyant force. And what when I let go of this object, will it go up, go down, or stay the same, and why? How much is the weight?
It's 0.
Yes. So what's 10 up and 0 down? If you add those two together, what's 10 up and 0 down?
10, so would it say the same?
10 up. So when I let go of this object, it's going to go up. Excellent, excellent, excellent. This drawing really helps, I think, separate the Archimedes principle from whether it's going to float or sink. I'm going to do something I normally don't do. I'm going to give away one of my test questions. It's not going to be exact, but it's going to be very similar. And what I'm going to have you do is I want you to think about it. And I love the question, but yes.
So you said floating is where it like stays the same?
Yeah, in physics, floating means you're not going up or down. So you can actually float under the water. Now, I understand in regular English lingo, we think float means to go up to the top. Now, if I have somebody down here, it starts going to the top, but it actually doesn't, our lingo, we think it doesn't float to us above the water.
So is there and sinking going down, so is there like a scientific term for going up, or is it just?
I would say if you have a net force up, you're going to accelerate up. If you have a net force down, you'll accelerate down. And if you have no net force, you'll just stay where you're at. So that's in terms of physics. All right, so let's try it. Now, I don't want you to get real close to your partner, but whoever you're sitting close to, I want you to think about this situation. I'm going to try to draw these as similar as I can. Now, just pretend that they're really the same size. I'm trying my best. So imagine they're all the same size. Oh, this is a little off. That's all right. Same size. Okay. Sit with somebody, and I'll give you about 2 minutes to talk about this whole situation and say, well, what kind of question could he possibly ask? Now, here's one of them. Which object do you think has the most mass, or you can't tell? Which object has the most weight, or you can't tell? Which one has the most buoyant force on it, or you can't tell? Which object has is displacing the most amount of water, or you can't tell? All right, there you go. Find somebody you can sit with. It can be 3 people, 2 people, and I don't want to give you the answer right away. I want you to talk about it, and let's see what happens the next. Let's see 3 minutes, okay? Let's do 3 minutes.
Yeah, they all have the same volume because they all displace the same. And then which means they're both. Well, if it's like they're all equal, considering you don't know what they have the same volume.
Is it because
Yes, you said more mass to have.
Yeah.
So if
Yeah,
if
I'd
were
say
all
that's
the
similar.
same
It's like with the
volume,
leader boxes, you know, like one can be nothing and one can be lead.
if they were all 1 liter,
You don't know, but you know that it's a leader or something.
We know it's volume, which means that mass is pretty edgy. No, because if they're made of something different, it's all. Oh, I see what you're saying.
So it's flat now?
Okay, they all look the same.
No.
I was thinking of
Wait,
like
actually, yeah.
greatest to least.
Even
Even
like
like
a
a
cell
cell
Yes.
We wouldn't be able to see.
The one that has the most mass. Okay, so you see real quick.
You wouldn't be able to tell the exact. You just know which one's the
You talk to somebody, Walker. Talk to somebody. Oh, you did? Okay.
Since the volume is
All right. Now, believe it or not, if you could have discussions like this when you study for the exam, you're going to do well. A lot of you don't like to do that because you're sitting around and you'd rather say, oh, I had A, and I had B. Oh, too bad for you. We had A. Let's move on. That's not the way you should do a peer group. And that's not what you should do here. So can you at least tell me, did you have any disagreement in your group at any time? That's good. That's good. If you had some disagreement, that was probably a good group. If you agreed on everything, either somebody took control and said, here's how it is, be quiet, I'll tell you how it is, and you may not have learned anything. So be careful about groups like that, okay? All right. Who would like to answer the first, let's see, I'll tell you the question you're going to tend to miss. Which one do you want to do? Which one? Who wants to pick one? Pick one and, all right, which one do you want to do? Which one of the question, and you have to explain it to me. Okay, I would start with that one. I like that.
We think they all have the same force.
Okay, now, your group says all the same. If you agree with that, raise your hand. If you disagree, raise your hand. Walker.
Same material?
No,
buoyant force.
Oh.
Oh, yeah. She said, they said all of them have the same buoyant force on them. What do you think?
Oh, I agree.
All right, does everybody agree with that? Okay, now, the problem with that is you have to be careful about a group. So no one in your group thought the buoyant force was different. Is that correct? Okay, so that's something, I'm glad we did this because you're all wrong. And I hate to make you think that way, but let's try it again. What used to be in this space right there? Water. That much water. Same amount of water. These have the same buoyant force on them. I agree, because they're both displacing the same amount of water. Now you have a problem. Aren't you? What if you had, first time you saw this question was on the test? You wouldn't like that, would you? And Okay, so which one has the most buoyant force on it? This one. And I'm going to draw those the same size. I have to draw this one smaller. And I have to draw this one, pretty small. All right, who wants to tackle the second question? Did we learn something? All right, let's do the next one. Next question. Another group. Sarah, your group. What do you want to do? How about, which one do you want to do? Weight? You want to do weight? Let's do weight. All right, I'm listening. You got to hurry just a little bit.
You said you can't tell.
What now?
You said you can't tell.
Can't tell. All right. How many people said you can't tell? Wait, even people in your group did not. Weren't you in her group? You didn't raise your hand.
Oh, well, Kinsley.
All right. Okay, so nobody agrees with your group. Who wants to try that again? Maybe you're right. Maybe you're right. Anybody have a different answer? Okay, Liam.
We said that they would all have the same weight.
Wait, you just said you did. They just said what you said.
Wait,
No. Okay.
Wait.
in, from greatest to least weight, DCBA.
What is it?
There we go.
The greatest is D, second C, B, then A.
Okay. All right.
D having the greatest.
All right. Let's try it. Ready? This one's laying on the bottom, so I believe its weight would have to be greater than the buoyant force. This one is floating, so its weight would have to equal the buoyant force. This is also floating. Its weight would have to equal the buoyant force. And this is floating. The weight would have to equal the buoyant force. So which one has the most weight? D. Look at the arrows. Next. C. B. A. All right. I only have 30 seconds, so I got to help you a little bit here. Who has the most mass? Well, if you're on the Earth and you have the most weight, you have the same answer, wouldn't it be? You have the same mass. Now, how about density? If you have the most mass in the same amount of space, most dense, less dense, less. What's the last question? Could these be made of the same material? No. You know why this object only displaced a little bit of water? It doesn't weigh very much. All right, excellent class. Excellent class. Thank you very much.